All right, hi folks, this is Larry Massimo. I wanted to record a video here for Math 241. This is the Module 9 homework, and I wanted to give you a few examples of some of the different kinds of concepts here in Module 9. The first one is what's called the U substitution method for integration. So, for integration, we use this power rule that says the integral of x to the n is x to the n plus 1 over n plus 1. And so this rule, of course, works when we have x to an exponent. But what if we have a more complicated scenario like this parenthesis being raised to the exponent 11? Well, this is where we use something called a U substitution. And in this example, they're actually giving us a nice hint of how to set up what is the U variable, the U substitution. If they didn't give us this hint, we would think to ourselves, well, we want to let U be the quantity, the expression in this parenthesis being raised to the exponent. Because our goal here is to take this messy integral and make it look like the integral of U to the n du. Because if we can do that, it then will be transformed into this power rule format, and we can write this as U to the n plus 1 over n plus 1 plus a constant. So we want to get U to be the quantity being raised to the exponent. So step 1, let U equal x to the third plus x squared. It's the expression in the parentheses. Step 2, now there's a couple of ways to do this. What I like to do is come up with an expression to substitute for this dx here. Because remember, we want to convert that dx into a du expression. Well, one way you could do that is take the derivative of both sides. So I'm going to take du dx, the derivative. So that's 3x squared plus 2x. All right, now I'm going to solve this equation for dx, meaning I'm going to get dx by itself. If I do that, I can multiply both sides here by dx. That'll cancel this out. And then du is 3x squared plus 2x dx, but I want to get this dx by itself. I'll divide both sides by this parenthesis. So this parenthesis cancels, so I'm ending up that dx is du over 3x squared plus 2x. All right, there's another way to do it, but this is the way I tend to do it because, again, I want to convert this dx into a du expression. All right, let me go to the starting integral. It was the integral of x to the third plus x squared to the 11, 3x squared plus 2x dx. Now, I want to do a u substitution. Well, what's in the parenthesis here is u, so this is u to the 11. I'm going to copy this parenthesis down for right now. It's going to cancel, but I'll just copy it. Now, let me do the substitution for dx. Well, that's where this expression comes in. Dx is du over 3x squared plus 2x. Well, now I can cancel out. I have a 3x squared plus 2x top and bottom. Cancel them out. I'm left with the integral of u to the 11 du. Well, now this matches my power rule version. So this is going to be u to the 12 over 12 plus a constant. But I don't want to leave my answer like this. Remember, u was just a temporary substitution. So let me go back to my definition for u, which was x to the third plus x squared, and I'll plug it in to get the final answer. I have x to the third plus x squared to the 12 over 12 plus a constant as the final answer on this one. Okay, so the starting step here is let u equal the expression in the parenthesis being raised to an exponent. Take du dx, solve for dx, then go back to the original integral and do the substitution. Your goal is to get the integral to look something like this. All right, let's take a look at another example like this. All right, here's an example. It's a little different. So they're giving me the integral of square root -1 plus 9s ds. Well, the first thing I'm going to do is replace the square root with exponent 1/2. Remember, the square root of x is the same as x to the 1/2. So let me do that replacement. So this is going to be the integral of -1 plus 9s to the 1/2 ds. All right, again, I'm going to use the u substitution method. U is this expression inside the parenthesis being raised to the exponent. So I'm going to let u equal -1 plus 9s. I'm going to take the derivative with respect to s. The derivative of -1 is 0. The derivative of 9s is just 9. All right, solve this equation for ds. ds is du over 9. All right, let me go back to the original integral. This parenthesis was u, so that's u to the 1/2. In place of ds, I'm going to drop in du over 9. All right, let me move this 1 over 9 out in front of the integral. Maybe that's a little easier. All right, well, now I can make use of the rule. The integral of u to the n is u to the n plus 1 over n plus 1. So there's going to be 1 over 9 u to the 3/2 over 3/2. Well, when you divide by a fraction, you can flip this fraction upside down and change the multiplication. So it's going to be 1 over 9 times 2 over 3 u to the 3/2. So this is 2 over 27 u to the 3/2 plus a constant. But again, I don't want to leave my answer in the u format. I'm going to do a substitution back because u is -1 plus 9s. So here's my final answer, 2 over 27 -1 plus 9s to the exponent 3/2 plus a constant. All right, so again, when integrating, if you come across a square root symbol, it's a good idea to change the square root to be exponent 1/2. All right, let me go to another example here. All right, let's take a look at this one. This one's a little different because the u expression here is really in a denominator. But here's what I could do on this one. Let me move this expression up to the top of the fraction. So I can think of this as the integral of x to the 6, 8 minus x to the 7 to the -2 dx. So I move the denominator up to the numerator. That flips the sign on the exponent from 2 to -2. Well, now this is looking like a u substitution problem. I'm going to let u be the expression inside the parentheses. So I'm going to let u equal 8 minus x to the 7. Take du dx. The derivative of 8 is 0. The derivative of x to the 7 is 7x to the 6. All right, I'm going to solve this equation for dx. dx is then du over -7x to the 6. All right, let me go back to the original integral and do some u substitution. Let me copy this x to the 6 down with me. It's going to cancel out in a second, but I'll just copy it for now. This parenthesis is u, so u to the -2. What about dx? Well, dx is du over -7 x to the 6. Well, now I have x to the 6 canceling. Here's an x to the 6 top, x to the 6 bottom cancel. Let me move the -1 over 7 out in front. So here is my integral to work out. I'm going to use the rule that says the integral of u to the n is u to the n plus 1 over n plus 1. So this is going to be -1 over 7 u to the -1 over -1. All right, here's a negative times a negative. That's positive, so 1 over 7 u to the -1 plus a constant. I don't want to leave my answer like this. I'll do a final substitution back because u is 8 minus 7x, so 8 minus x to the 7 to the -1 plus a constant for the final answer here. right. Let me go to an example that's a little different, which is called an initial value problem. And so you may remember we did some of these previously, but the difference now is we're going to need U substitution for this example. So they're giving us ds dt is 12t 3t squared minus 1 to the third, and they're telling us s of 1 equals 2. All right, well, really what they're asking us to do here is find s. Notice here our answer is going to be based on s. Well, the way I could do that is I'm going to integrate both sides. So s is going to be the integral of 12t 3t squared minus 1 to the third dt. All right, well, let's go ahead and use u substitution. U is going to be what's in this parentheses. So u is 3t squared minus 1. du dt is 6t, I think, right? Yeah. This 2 comes down and multiplies with 3 to get me a 6. So du dt is 6t. But I want to get a replacement for this dt expression. So dt is du over 6t. All right, let's write the integral now here using u substitution. Let me copy this 12t down for right now. This parenthesis was u, so this is going to be a u to the 3. dt is du over 6t. Well, 12t over 6t is a 2. So this is 2 integral u to the 3 du. Well, that's just going to be 2u to the 4 over 4 plus constant. All right, so s is 1/2. Now, u to the 4th, I want to replace u with its original expression, which was 3t squared minus 1 to the exponent 4 plus a constant. But I'm not done yet, because when they say solve the initial value problem, they want you to find a numeric answer for c. They don't want you to leave the constant as just capital C. They want you to actually find a numeric value. Well, that's where this s of 1 equals 2 comes in. They're telling us that when t is 1, the value of s is 2. Let me plug those values in, and I can solve for c. S is 2, and the t value is 1. All right, let me go inside the parenthesis here. This is 3 subtract 1, which is a 2. I'll finish it over here. So 2 is 1/2. 2 to the 4th is 16. 1/2 of 16 is 8. I'm going to subtract 8 from both sides to solve for c. So it looks like c is -6. So I'm ready to write the final answer now. I'll take this, this answer I had here and rewrite it to just replace the c number with -6. So final answer s is 1/2 3t squared minus 1 to the 4th minus 6. All right, so initial value problem will give you enough information so that you can work out a numeric value for the constant c. All right, let me do one more example. One other concept here is finding the area between two curves. And the area between two curves, I'm going to set this one up for you, but I'm going to let you do the integration. When you want the area between two curves, you take the integral of the top curve minus the bottom curve, dx. So for example, if I had something like, a curve here, f of x, and a curve down here, call it g of x, and here is x equal a, x equal b. Imagine I want to find the area between these two curves, it would be the integral from a to b of f of x minus g of x. So that's the basic setup. Now, the tricky part of this example is the top and the bottom curves are changing. So if I think here of area A versus area B, I'm going to have to treat these two areas separately because the top and the bottom curves are changing. Now, it's a little tricky, but what they're trying to show you here is the purple curve is given by this function, and the black curve is given by this function. So let's find area A. Again, I'm going to set up the integral. Area A is the integral. Let's see, the left bound is negative 3. The right bound is 0. The top curve is 2x to the third minus x squared. I think it says minus 12x. So this is the top curve. Now I'm going to subtract the bottom curve. That's the negative x squared plus 6x. And I can work this integral out and get a numeric value. All right, let's work out area B. Well, there, the x value is going from 0 to positive 3. The top curve now is the purple curve. So the top curve is negative x squared plus 6x, and the bottom curve is the black curve, which is 2x to the third. Maybe it's blue. I think that's blue instead of black. Anyway, it's 2x to the third minus x squared minus 12x dx. The total area you want as your final answer is adding area A plus area B. Okay, so the key to this problem is really treating these two areas, area A and area B, as separate areas. The reason you need to do that is the top and the bottom curves swap between the left side and the right side of this area they're highlighted. All right, hope this is helpful as you're working here in Module 9.